Let's look at compound interest compounded annually. Suppose you get a graduation gift of $1,000. You deposit it into an account which grows at 5% annual interest compounded annually. How much do you have in 40 years? We'll use this formula. If we deposit P into an account which grows at an annual interest rate of R is expressed as a decimal, compounded annually, then after T years we'll have F equals P times 1 plus R to the T. Again, F is the future amount of money, what you have in the future. P is the present amount of money, sometimes we call that principal. R is the interest rate, and T is the number of years. So in this case, what's F? We don't know what F is. We want to know what future amount we end up with. So F is just one big question mark. P is what the amount we start with. That's $1,000. R is the interest rate expressed as a decimal. So yes, I know R is 5%, but don't write R equals 5. We need to express that percent as a decimal. So R, 5% expressed as a decimal, is 0.05. And T, the number of years, is 40. Just go ahead and plug these into the formula. So P times 1 plus R to the T, in other words, it's 1,000 times 1 plus 0.05 to the 40th. If you type that onto your TI-83 or whatever calculator you have, press enter, you get $7,039.99. That's cool. You deposit $1,000, let it sit for 40 years, and you end up with roughly $7,000. Now suppose you want to take a blockbuster vacation 30 years from now. Suppose you want to have $15,000 in order to do this. How much do you need to set aside today if you want to have $15,000 in 30 years? Assume your investment grows at 7% annually. 7% annual increase is a reasonable rate of return over the long term. Okay, now notice this problem is different. Again, we use the same formula, F equals P times 1 plus R to the T, but notice this problem is different. In the previous problem, we knew what we started off with. We knew we started off with 1,000. We didn't know what we ended up with. This problem is just the reverse. We know what we end up with. We end up with $15,000. We don't know what we start off with. So in this problem, we know F, but we don't know P. The previous problem was just the reverse. So in this case, F equals $15,000. P we don't know. R, the interest rate, expressed as a decimal, is 0.07. And T, the number of years, is 30. So plug those into the formula. 15,000 equals P times 1 plus 0.07 to the 30th. Divide both sides by 1 plus 0.07 to the 30th to get P equals 15,000 divided by 1 plus 0.07 to the 30th. Now, if you enter that in your calculator, you get $1,970.51. Now, besides growing bank accounts, we can use these formulas to analyze growing populations or prices which grow at a certain rate of inflation. For example, in the April 2010 U.S. Census, the United States population was 308,745,538. Now, in recent years, the U.S. population has grown at an annual rate of 0.9%. If this trend continues, estimate the U.S. population in 2020, when we'll have our next federal census. Okay, again, use the same formula, whether it's a growing interest, a growing bank account, or a growing population, we use that same formula. In this case, F is what we don't know. We don't know what the population is going to be in the future. We know what the initial population is, 308,745,538. R equals 0.009. Now be careful. An interest rate of 0.9% means, when expressed as a decimal, is 0.009. Again, when you take an interest rate expressed as a percent and express it as a decimal, you move the decimal point over 2 spots. So we end up with 0.009. And T is 10. Plug everything in. We get 308,745,538 times 1 plus 0.009 to the 10th. And that turns out to be 337,685,453 people.